What if I told you that some of the smallest black holes in the universe just got a second chance at life? And what if the universe itself is telling us that dark energy might be switching signs, like a cosmic light switch? Welcome back to Cosmos and Cosmology. I'm your host, and today we're diving into a research brief that reads like a scientific thriller. Two independent papers, published on the same day, have converged on the same shocking conclusion. The Poltergeist gravitational wave signal, which was supposed to rule out ultralight black holes as dark matter, is actually suppressed by a phenomenon called critical collapse. The ultralight primordial black hole window is wide open again. But that's not all. We've also got a sign-switching dark energy model that fixes the negative neutrino mass problem, a self-supervised AI that can detect supernova gravitational waves without any labeled training data, and a dark matter subhalo detection that's about to test our best theories of dark matter. Stay until the end, because by the time we're done, you'll understand why the universe might be weirder and more interesting than we thought. Let's start with the elephant in the room: primordial black holes. These are black holes that formed in the first fractions of a second after the Big Bang, not from collapsing stars. They are a perfect dark matter candidate because they don't require any new particles, just gravity. But here's the problem. A few years ago, researchers discovered a gravitational wave signal called the Poltergeist. This signal was predicted to come from ultralight primordial black holes with masses less than a millionth of the Sun. And the Poltergeist was loud, so loud that it seemed to rule out these tiny black holes as dark matter entirely. This was a big deal because ultralight black holes are one of the most elegant explanations for dark matter. If they are ruled out, we're back to square one. But here's the thing. The Poltergeist calculation assumed all black holes had exactly the same mass. That's like saying every single grain of sand on a beach is exactly the same size. And that assumption, it's wrong. Two independent papers today, 2605, 21477, and 2605, 21474, converge on the same result. When you account for the fact that primordial black holes don't all have the same mass, the Poltergeist signal disappears. Here's why. When black holes form in the early universe, they don't all come out the same. There's a process called critical collapse, which produces a universal low-mass tail in the black hole mass function. This tail scales as mass to the power of 378. What does that mean? Imagine you're at a concert, and there's one person screaming. That's the Poltergeist. But now imagine that person is joined by thousands of others, each whispering. The whispers drown out the scream. That's what's happening here. The low mass tail from critical collapse produces a sea of tiny black holes that generate their own gravitational wave background, which overwhelms the distinct Poltergeist signal from the monochromatic population. One paper, 2605, 21477, shows this suppression directly. The other, 2605, 21474, decomposes scalar-induced gravitational waves into 8 distinct channels and shows the same thing. Include the Choptwick mass spread, and the Poltergeist vanishes, replaced by a different, scalar-induced background. So what was once considered ruled out, ultralight primordial black holes as dark matter, is now viable again. The window is open. But that's not all. Let's talk about neutrinos. The standard model of cosmology, lambdictum, has a problem. When you combine data from the dark energy spectroscopic instrument, the cosmic microwave background, and supernova, you get a best-fit neutrino mass that's negative. That's unphysical. Neutrinos can't have negative mass. It's like measuring your height and getting -3 feet. So what's going on? Paper 2605, 21456 has an answer. Maybe it's not the neutrinos.